Well, that's the idea. The idea is, the questions will prompt you to go like, okay, do I understand this concept? Maybe not entirely. Maybe I should go back either to study, look it up, and you know. So that's the idea of the homework assignment. Okay. So we're gonna go over the questions one by one. Question number one. Consider the not equal to relation over all integers, because I have to be very clear of what the relation is defined over, because that can change the property as well. Which of the following relation properties apply? So, okay, let's check out each one first, okay? Antisymmetric is not equal to antisymmetric. What makes something antisymmetric? That is the first question. What is the definition of antisymmetric? Okay. So, ARB and BRA implies A equals B. Okay, so we have not equal here, okay? So does ARB and BRA implies A equals B? Definitely not in this one. Okay. Is it transitive? Okay, what does it mean? ARB and BRC implies ARC. In this case, totally not the case, right? A does not, 1 does not equal to 2, and 2 does not equal to 1. Does 1 not equal to 1? No. So it does not apply, right? Is it reflexive? Is each integer not equaling to itself? That would be false, right? So it's not reflexive. Is it symmetric? If A does not equal to B, can we conclude that B does not equal to A? Yes. Yep. Okay. It is finally symmetric. Does it have any type of ordering?
No.
It has no antisymmetry, so it cannot be any one of the ordering, so it's just symmetric in this case. So are we okay with question number one? Why it is just symmetric, but none of the other properties? Okay. Next one. The next one is equal to. Okay, so we are looking at equal to defined over integers. And we want to look at, okay, let's not do partial ordering first, because that is something that we can answer only after we look at the other ones. First of all, is it reflexive? Is each integer equaling to itself? Yes. Okay. Is it antisymmetric? So if A equals B and B equals A, does that imply A equals B?
Yes.
Yes. Okay. Is it symmetric?
Yes.
It is symmetric. Why is it symmetric? If A equals A, then A equals A. A equals A if and only if A equals A.
It could also be another strength that it is reflexive already.
No. Reflexive by itself does not imply it is symmetric.
I know, but the fact that you can switch them around, you have the same.
Right. It is only because you can switch one ARB implies if and only if BRA. That is the definition of being symmetric.
Yeah.
And equals to has that property.
What I was thinking is the fact that it is reflexive, you can switch the element around, or it is the same element.
You cannot switch the elements around. I don't understand what you mean.
You say ARA and ARA because it's the same.
It is still the same definition for symmetric. It is still the same property for symmetric, because symmetric basically says ARB if and only if BRA for all pairs of elements in the set, right? So if you choose A and B to be the same thing, then ARB if and only if BRA works, right? But what if A and B are different? Then ARB itself is false to begin with. But that's okay, BRA is also false. So the if and only if still works, because they are both false. The only problem with symmetric is when one is true, but the other one is not. In other words, you can find me a case where ARB is true, but BRA is false. Then it cannot be symmetric anymore. Okay? Is that okay so far? Is it transitive?
No.
If A are B and B are C, does that imply A are C?
Yes.
The answer is yes. It is also transitive, which means it is partially ordering. Because we have all the elements for partial ordering, it is reflexive, it is antisymmetric, and it is also transitive. So those three implies it is partially ordering, but is it total ordering?
No.
Because the equality is not defined between all elements in the set. So it is not total ordering, or it's not totally ordered. Is that okay? All right. Moving on to the next one. This is one of my favorite ones. If R and S are both relations defined over some set X, and we also know that R intersecting with S is reflexive, then what do we know for sure about R? Okay, so let's go through this part here. Can we conclude that R is transitive? No. We cannot make that conclusion because there's nothing in here that suggests anything about whether it's transitive or not. So we cannot say that. Now, is it reflexive?
Yes.
Can we claim that R itself is reflexive?
It has to be. Yeah.
It has to be, because what is in the set of intersection?
Reflexive.
What is common between the two sets, right?
Yes.
So if what is common between R and S is reflexive already, then each one, not just R, but S has to be reflexive as well. Okay, so that's the only answer, because because this is not one of the multiple select multiple answer type of question. There's only one that can be correct. So the correct answer is just R is reflexive. I like to throw in this thing here just to make people think, can it be none of the above?
Just to let you know, I didn't check that answer.
Okay.
But I did still get it wrong though.
Well, there are many ways to get it wrong, so that's okay. Question number 4. Consider the less than relation over all integers. Which one of the following relation apply? Okay, first of all, is it reflexive? Is every single integer less than or equal to itself? Yes, it is.
Wait, it's not equal less than.
Oh, it's just less than. Okay. I read the question wrong. Okay, it's just less than, so it's not reflexive. I'm sorry. I apologize. Yes, I'm recording. I admit to my own mistakes. Not a problem. It's the quickest way to get out of that sort of situation. Yes, I did it. So.
That's a bit unexpected.
Yeah. I learned it from Willie Brown. Okay, look it up. Okay, is it symmetric? Is less than symmetric. If A is less than B, if A is less than B, if and only if B is less than A. Does that make sense to you? No. So it's not symmetric. Is it antisymmetric? Now this is a really tricky one. Is it antisymmetric?
It's always false on one side.
It is antisymmetric.
Yes.
Okay, why is it antisymmetric? Because antisymmetric says if A are B and B are A, then A equals B, right? Okay, so give me a case where A are B and B are A. You guys would say, well, that's not possible. It doesn't happen. So that means the left-hand side of the implication is always false, regardless of which A or which B you choose, right? So what happens to the implication itself?
Becomes true.
The implication becomes true. So that means it is antisymmetric, because the left-hand side of the implication is always false. That makes the implication always true. Okay, so this is a really tricky one. Is it transitive? Yeah, it is transitive.
Wait, how is it transitive?
Because if A are B, if A is less than B and B is less than C, does that imply A is less than C for integers?
Oh, okay. All right.
That's transitive.
Okay.
The answer is yes, it does imply that. So as a result, it is transitive, it's antisymmetric, but it is not partially ordering because it is not reflexive. It has to be reflexive as well in order to be partially ordering. Okay, moving on. Question number 5. Consider the greater than or equal to. So this time it is an equal to. Is it transitive?
Yes.
Yes. Is it symmetric?
Yes.
Wait, is it?
It is.
Oh, okay.
No, it is not symmetric.
Oh,
It is reflexive.
yeah.
Oh, what?
Okay, it is not symmetric because symmetry means if A is less than or if A is greater than or equal to B, then B has to be greater than or equal to A. That does not apply for all elements in integers. So it's not symmetric. Is it antisymmetric?
No.
If A is greater than or equal to B and B is greater than or equal to A, does that imply A and B are the same?
Yes.
Yes, indeed. It is antisymmetric. And because it is transitive, antisymmetric, and reflexive, it is also partially ordering. So now the question is it also totally ordering? In other words, if I pick any two elements, any two integers, A and B, okay, can I say that at least we know that A are B or B are A? The answer is yes. Okay, at least one of the relation has to exist. So it is also totally ordering. That is for greater than or equal to. Moving on to question number 6. If R is a relation defined over X, if it is known to be reflexive, which of the following do we know for sure, regardless of how we define R and what X is? This one is there's only one correct answer. So we are looking at the cardinality of the two sets. Okay, the cardinality of R is greater than or equal to the cardinality of X, equal to, less than, not equal to, or none of the above. None of the others. Which one?
Greater than or equal to.
Greater than or equal to. That is correct. Because in order for a relation to be reflexive, then for every single element in X, whatever the element E is, ERE has to exist. So that means whatever number of elements you have in X, R has to be at least as big as that. Now, can R be bigger? Absolutely, but it has to be at least as big as X in terms of number of elements. So once again, I throw in one of these, none of the other answers.
This one was confused, I ain't gonna lie. This one was kind of confused, I'm not gonna lie.
What makes it confusing?
If R is relation defined over X is equal to this question. That's why I didn't.
Regardless of the actual definitions, that means it doesn't matter how you define R and X. Which one of these has to be true?
So you have to find the least
In all cases.
In all cases, exactly. Yep.
Can you give an example of a relation that would be greater in cardinality than
It's reflexive, but the relation R itself has a cardinality that's greater than the cardinality of X. If you take a subset of integers, like 1, 2, 3, 4, 5, okay, greater than or equal to is going to be one of those things. Because every element 1 is greater than or equal to 1, 2 is greater than or equal to 2, and so on. But you know what? 1 is all, yeah, exactly. 2 is greater than or equal to 1, 3 is greater than or equal to 1, and so on. So that's what makes it greater than or equal to. All right, are we okay with 6? Okay. Let me double check and make sure the recorder is on, and yep, so it's on, and we got audio. That's good. Okay, number 7. So 7 is asking if R is a relation defined over R, and R is known to be symmetric this time. Which of the following do we know for sure has to be true for sure, regardless of how, in all cases, okay, regardless of how R and X are defined. Okay, so which one did you guys choose? Now this one is kind of tricky because we know a very specific case of a relation that is also known to be symmetric, and that will give you an idea. Okay, so let's check out these things here and see if it makes sense. Okay, the cardinality of R is twice the cardinality of X. No. The one example that I was thinking about is the empty set. the anti-relation is symmetric. Okay. But then is R always guaranteed to be less than X, or the cardinality thereof? Nope. Not equal to?
Nope.
Nope. Equal to?
Nope.
Nope. Even?
Nope.
Odd?
Nope.
Greater than or equal to?
Nope.
Okay, well, we don't have a choice this time. It is one of those cases where none of the other choices apply.
It had to be the last one.
This one you.
It's a psychological thing, right?
Yeah.
Well, psychological things should have nothing to do with programming, right?
I don't know.
You just have to answer each question objectively. You know, if that is the answer, it is the answer. All right. So did I get? Yep, I got 7 out of 7.
Wow, man, you're a genius.
No, and one of you actually corrected one of my grading mistakes. You know, so that was pretty good. All right. Any other questions about this quote unquote assignment? It's basically a week-long quiz. I mean, it's like. So, are there any questions about this one?
Are those too similar to the questions that are going to be on the exam?
I have not decided yet. But it will test your knowledge, you know, about the same kind of stuff. Yep.
I have a question about the exam. Like,
Mhm.
what would it take to get a A grade question answer? Like, if you'd have one of these questions on the exam.
You have to basically answer the question. You know, in every aspect of your answer, you have to address exactly what I'm looking for, and it has to be correct, 100%. So other than that, it's hard for me to describe, you know, what makes a perfect score answer. Yep.
How many questions do you need to test?
I have not decided yet. It all depends on the complexity or the difficulty of each question. If I ask a lot of easy questions, then it's going to be more. If I ask, you know, harder questions, then there'll be fewer. Yep. And don't ask me, you know, how I gauge as hard or easy, because you know, I have used that answer before, and most people disagree with my assessment. Any other questions? Yep.
Those last two relations questions.
The last two.
Yeah, the two relations cardinality questions.
Yeah.
Do you have any advice on how to do those?
Okay, so let's go back to look at those questions and find out, you know, what to do about those. Okay, so you're talking about the last two questions, right?
Yeah.
The ones about cardinality. So, one way is to look at each possible choice, and then you ask yourself, can I find a case to confirm this, and can I find a case that makes this possible? Okay. So the use of the empty relation, because we know the empty relation is symmetric, and that's actually the most, if I remember correctly. So the empty relation will basically rule out many of these choices already, right? So it will rule out the equality, it will rule out the inequality, because what if X itself is also an empty set? X can be empty, right? So if X is empty, R has to be empty. So yeah, but R will still be symmetric. The rest that we cannot rule out, but be equal to 2x, we can rule out as well. So I'm using examples to help me rule out possibilities.
So it's kind of a elimination by guessing.
Not really so much guessing. It is systematically go through examples that I can think of in order to rule out, you know, certain possibilities. So that's the nice thing of multiple choice, is you can eliminate the ones that cannot be the case. So when you narrow it down to, you know, just a few cases, if you run out of time, you can randomly guess, but your chances of guessing the correct one is already significantly decreased. But the exam is going to be all open-ended, so you cannot use that strategy.
And then are there a handful of relations that end in?
Yeah, In this case, the focus is symmetric. So you want to think of all the relations that are symmetric, but then you also have to think about relations that are symmetric and something else. Okay. For instance, greater than or equal to is not symmetric, so you don't even need to think about that. Equal to is symmetric. Not equal to is symmetric. So you think of examples that are symmetric, and then you try to think of, okay, would that apply, would that apply, would that apply? So other than that, I could not really think of, cannot describe the thinking process any further than that. It's basically a process of elimination. Does anyone want to add to that? Because my thinking process may not be the same as yours, but it doesn't mean that mine is the only way to do it. Does any? Yeah, go ahead.
I'm not sure if I caught this. When you said that the set is empty, R is also empty.
Yes, because if X is an empty set, then R, there's no way you can define R to be anything other than the empty set. Because remember, R has to be a subset of X multiplied by X. So if X is an empty set, then the Cartesian product of X and itself is also an empty set. And because R has to be a subset of an empty set, R has to be an empty set as well. Okay. So there are these extreme cases, that will help you kind of like, okay, rule out this one, rule out this one, rule out this one. So whatever is remaining, you just have to kind of think about it and go like, can I rule this out? Can I find a case that is symmetric but not that? So other than that, I can't really, describe the thinking process. How many people did a personality type test of this class? If your stack, okay, well actually I shouldn't say stack because the MBTI does not use that. If N is one of the letters of your personality type, it helps. Yeah, N is intuitive. It is the opposite of sensing. So sensing is great if you are taking a class in history or organic chemistry, because sensing means you typically have good memorization skills, and you can just remember things. I mean, that's just the strength of people who are quote unquote sensing. Intuition are people who can intuitively understand concepts. Okay, they can make connections without logically thinking about things. Okay, that's one way of looking at N. The other way to look at N is those people. Some of those people also explore possibilities. Without actively logically thinking, their mind just kind of branches out and look into possibilities. So that's the N talking. Neither is better than the other. Okay, so there's no relation defined between N versus S. They're just different. I guess different from is a relation too. But understanding your own personality is helpful, because that means if you know this is who you are, and this is what is required of you to do, then you know how to compensate if it is not going to be one of your strengths. I don't want to turn this class into an MBTI, discussion. Some of you probably have looked into that stuff a lot already at this point. All right, so that's one, and then the other one is the one right on top of it. It's the same way, I just look into the elimination of the answers that cannot be, and then whatever is left. This one is actually a little bit different. This one, you can kind of look at it in a different way, because the requirement of reflexive is every element has to relate to itself. So you know that there are at least as many elements in R as there are elements in X. So equal to and greater than or equal to are the only two choices left. Because less than cannot be, not equal to cannot be, because you can have a relation that is just reflexive. Or is it? Yeah, just reflexive. Yep.
So for the last question, to explain why R is
The next question. Okay, what about this one?
Could you explain why R is not even?
So why this is eliminated?
Yeah.
What if X only has one element? So that's another special case. When X itself only has one single element, what can R be? R can be empty, right? But if R is not empty, what is the only other choice? R can only has one single element. So when you look at the question, can R be symmetric? Well, the empty set can be symmetric. Well, empty is even, okay? But if R has one single element, let's say A, and you define ARA in the relation, is that relation still symmetric? Yep. So I can eliminate that as well. I cannot really describe the process, of okay, why I cannot describe the process in my head to think of that special case. It's not like I have thought of all these special cases before. When you asked me that question, that's when I started to think about it. So I cannot describe the thinking process beyond the fact that I just explore different options until I can find one that rules out that possibility. If you're interested in dissecting the thinking process, I suggest that you watch more episodes of Sherlock Holmes. Yeah.
What about reading the novels of Sherlock Holmes and Lupin the Third? What about Lupin the Third and Sherlock Holmes?
I think Lupin the Third may get you into some trouble.
Okay.
And yeah. And claiming to the police or the court that I got this idea because I watched this anime may not be a good way to get yourself out of a situation.
We talk about the original
okay.
Lupin. Yeah.
Oh, okay.
Like, I was into the piece before the anime came out. My jaw dropped when I first saw the anime. I was like, wait, they have an anime about this? Mama.
Yep. They sure do.
Huh?
All right, so we are done with relations, and Aleph Null is done too. Okay, so I'll give you guys some activities maybe later. But we did go through questions in the practice exam that ask questions about Aleph Null. So that kind of gave you, some exercise, to think about Aleph Null. Yep.
Isn't Aleph Null is just the highest number we can count to?
Say that one more time.
It's because when I did some side research on Aleph Null, now I'm just trying to make sure it's lines up correctly. Aleph Null is just a really big number. It's the number of infinite, isn't it?
Aleph Null is defined by definition. Aleph Null itself is the cardinality of a set of natural numbers.
Okay. So
That is as simple as it gets, right?
right.
But the discussion of Aleph Null is not simple because how do we know that another set also has the same cardinality as the set of all natural numbers?
Right.
So for certain things it may be easy, but for certain things, other things it may not be as easy. Like we proved that integers, the set of all integers, also has the same cardinality of the set of all natural numbers. So that by itself doesn't make a whole lot of sense because natural numbers has one end that is definite, the other end goes indefinitely, right? Integers can go in both directions indefinitely. So how can they have the same cardinality? Well, we just kind of fold it. One side, take all the even numbers. The other side, once it's folded, we'll take all the odd numbers. So now we have, a way to convert, right, all integers into just natural numbers. But it works the other way around as well. We can give, if I give you a natural number, you can map it back into integers. So the bijective function idea is important because any set that has a bijective function to map to and from natural numbers also has a cardinality of Aleph Null. That becomes the really difficult or tricky part is, can you find that bijective function? If I give you a set, okay, and here's all the natural numbers, can you find a bijective function to map between the natural number and the set that is in question. That becomes the most difficult part of analyzing whether a particular set has a cardinality of L null. But in the notes, we talked about how I can fold 2D space into 1, and then in the practice exam, we talked about how we can fold 3D space into 1, okay, and how we can actually reverse the whole process. So that is counterintuitive because you think of the 3D space to be quite a bit bigger than a single line of natural numbers, but as it turns out, there is a way to map those two in a bijective way. So that's kind of the essence of Aleph No. All right, so if there are no questions, we're going to move on to propositional logic, which is not a very big slide. It used to be a lot bigger. I simplified the discussion because certain things are just not really useful. Yep.
Will the test cover some of this, or
No, the test only will end with Aleph No. Yeah, so that's it.
So you do need to study Aleph No, though.
Huh?
You do need to study Aleph
You
No.
do need to study Aleph No. That is correct. And the exam is next Monday. And it's open book, open notes. We talked about it already. Are there any questions about the logistics of the exam?
Do you need to bring any Scantron or?
Nope, no Scantron. You might want to bring extra paper with you. So, bring extra binder paper, for instance, because, I will give you space to write your answer in the exam itself. But if you run out of space, you might want to have extra pieces of paper instead of having to ask around or have me to go to the office to get you some extra paper.
Hey man, at least be a good workout.
Yeah, but you lose time too.
Oh yeah, that's right.
Yeah. So just bring extra pieces of paper. Make sure you have pencils, writing instrument with you. There was one exam like this where a student came in without a pen or pencil and asked me, "Do you have a spare pencil?" And we're like, "No, I usually do not use pencils." Okay. Any other questions about the exam? You can ask for clarification during the exam. If you're not sure what I'm asking, you can basically ask me, okay, what is exactly being asked about this question, but I cannot answer the question for you. Nor can I answer any questions about notations that we have already talked about in class or defined in the modules. So that is something that you have to kind of take care of. For instance, if I give you something that has this particular symbol, I cannot answer the question of what does that mean? I cannot answer that question because it is already used quite a bit in this class. Okay? So anything that you can find in the notes in the module and anything that I have talked about in class, those definitions, I cannot answer those. You can, I cannot answer the question of what is injective.
What year was injective? No,
You can ask that question today.
okay.
And my answer is read the notes. Or watch the video. Or go to YouTube. I'm pretty sure if you type in injection or injective function in YouTube, you will find
A lot of them, yeah.
20 plus videos that will talk about the same thing.
More like 300 plus. I tried.
You tried? Okay,
Yeah, it's
cool.
300 plus.
All right, so we are moving on to propositional logic, which is interesting. Yep.
One last question about the test. You were talking about the symbols. Are we, because on the first day we went over like 4 different ways to write the same symbol. Are we going to need any more than the ones that we normally use in the lectures?
No.
Okay, good.
Yeah, I'll just be using one of those 4.
Oh, so we do need to memorize all 4.
You need a cheat sheet to tell you, okay, these are the alternatives. Or you can just print out that module.
I will.
Yep, print out that module and bring it with you. That's the idea of an open book, open notes exam, right? I mean, you can bring whatever you want to help you in the exam. All right, so propositional logic. Okay, it is a part of a computer science class, cisp440, But do you think propositional logic existed before computer science, before we had computers?
We went over this. This existed before the machine was invented.
Okay, so who came up with propositional logic?
That I don't know.
I don't know either, but I'm
Oh.
asking you guys. But that's why I'm asking you guys. Because some of you have taken philosophy, right?
Oh, yeah.
So in philosophy, they talk about propositional logic, and they talk about the early philosophers. Okay, so who came up with propositional logic?
Plato, wasn't it?
Plato, Socrates,
Kind of like proposition is
One of those
kind
One of the
sentence.
Greeks, right? So
Okay.
it has existed for a long time already. What is the reason? Yep.
I was thinking proposition in other languages like Latin-based languages would be a sentence.
Okay. Well, sentences, that's where it came from, but the logic itself, so that brings us to the next question. What is the purpose of the study of propositional logic? Yep.
To determine what is true or not true. What is correct or incorrect reasoning.
Okay, so reasoning. Okay, I like that word. Okay, so it's basically describing it's a skeleton of reasoning. Okay, the framework of reasoning. How is this different from your usual math, like calculus or algebra? I know it's related, but how is it different?
Questions like, is it reversible? Can you say one thing and then repeat it back?
Well, this forms the framework, behind mathematical proofs as well. Okay, so it is really kind of important. I used to have slides. I removed that slide about what is truth. Okay, because it's more of a philosophical discussion. So in this case, propositional logic is based on propositions. A proposition is a condition that may be true or false. Now this is really important because when I make a certain statement like A and B, I'm not asserting that A and B is true. I'm just asking, is A and B true or false? I'm asking a question. Okay? Propositional logic is a logic system. It is a system that can prove whether a particular proposition is either true or false using a somewhat mechanical method. So this part is what relates to computer science. Okay? In the early philosophers, they studied this, more or less, as a philosophy, as a philosophical type of issue. But we study this not from a philosophical perspective, but from a practical perspective. So what do you think is the practical perspective to propositional logic, or logic in general, in computer science? Why do we need to know about this sort of thing from a practical standpoint? Conditional statements, okay. Well, conditional statements are very important in programming. What else?
So we know our program's gonna work in every case.
Aha, I like that. Okay, so we know whether a program is going to work in all cases, or at least based on the constraint of the input, we know it's going to work, right? And in return, why is that important? I mean, you guys know already. I just wanted to crash. So it doesn't crash. Okay, crashing is not the worst that the program can do, not in today's world.
The wrong answer.
The wrong answer is not the worst either.
Oh, you said no.
Yep.
So that we may structure it in such a way that it makes sense for it to be a certain answer.
Okay. That you're all of these answers are great, but the actual answer, I'm going to give you some examples. Yep.
So that it can be exploited.
Cannot be exploited. I like that. So the first one is hard bleed. Okay, most people have forgotten about this one already.
I never heard of it. That's the thing.
Oh, okay. Well, Valentine's Day just passed. Okay, because I was thinking about using this as a symbol. So the hard bleed bug is a really significant one because it has to do with the OpenSSL secure socket layer library, which is at the basis of a lot of HTTPS communication. Okay, and the hard bleed bug basically allows a prober, a hacker or cracker in this case, to basically get the keys of a SSL engine and as a result, you can break encryption. Okay, you can also get the passwords and so on and so forth. Basically, it opens up a window into the memory space of that particular engine. So that's bad. Okay, so the question is, how did it happen, right? You can read about how it happened, but what we are going to talk about also applies to hardware. This is a software issue, but the hardware issue is even more insidious in many ways. The most recent one is which one? Meltdown and Spectre. That's right. So Meltdown, Spectre. Why is the networking business dozing through Meltdown, Spectre? Because they cannot do a single thing about it. That's why. So we got Meltdown and Spectre. Both of these are hardware-related issues. Both of these are caused by what we call a race condition in the hardware aspect of a computer. But all of these relate to what we are talking about, at least a little bit, because why do you think they are related to what we are talking about at this point?
Help prevent exploits like this in the future.
What is an exploit? At least, can someone summarize, what is an exploit?
It's using a vulnerability.
And how does a vulnerability exist? How does it,
Overlook
why is it there?
because someone lapsed in judgment. You didn't notice the fault.
Okay.
Someone did propose
Yeah.
it might be a fault. Didn't test it.
Did not test it. Okay, so I like that too. So when you test it, you will find that the software is going to,
Malfunction. I was gonna say when something is used outside of its intention.
well, you can always attempt to use something beyond what it's intended for. The question is the software going to behave erroneously? Or just say, slap, not gonna do it, right? That's the question. So if you design, like the OpenSSL library correctly, and you send in a packet that is incorrect, that is not reasonable, what do you think the server is supposed to do? Whack, right? Not gonna answer that one. But instead, it answers the request. And because of the way it's coded, it also discloses memory content inside the library, which is really bad. Okay? So it boils down to one thing. Okay? Can you first of all, can you define the proper behavior of a program? Okay? And that includes both behaving correctly when the correct and legal request is coming in, but it also defines the behavior. What if the request is not well formed? What if the request is not proper? What am I going to do about it? Well, you have to recognize that request is not well formed, it is incorrect, it is invalid, and then the second thing is don't do anything about it. Okay? Or if you do something about it, you log where that request is coming from. What is the IP address? You try to do a back trace immediately and find out how it bounces off multiple routers to get to your server. You try to collect as much information as possible, but you have to flag it, right? That's the proper behavior. So now the question is, now that you can define what the program is supposed to do, this is the program. How do you prove that this program is going to do exactly that? That becomes the biggest question. How do you do that? Propositional logic is a starting point, okay, but it does get you into the mindset of what we call automated theorem proving. Okay? Okay, so let's look that up too. Okay? Automated theorem proving. We have some of these already. So if you look up automated theorem proving, it summarizes, right? This is a subfield of automated reasoning and mathematical logic dealing with proving mathematical theorems by computer programs. In other words, to verify, to validate that a program is going to do only what it is supposed to do is by itself a long, gigantic proof. We're not going to do that in this class, and most of you probably will not take a class in that area unless you go to a school where such a class exists. But it is important because it also leads to automated program verification. So automated program verification, which comes in many, many different names as well. Okay, so program verification is based on automata, the notion of, okay, that's a little bit too researchy. But that's the area where you can feed a program into the input would be a program, source code in C, C++, whatever programming language. Mathematical description of what the program is supposed to do, what is supposed to be the input, what is supposed to be the output. And then the output of this entire program is one of two possible answers. Yes, the program is good to go. No, somebody has to fix it. Okay? If it's yes, the program is good to go, it means you don't have to throw test cases at this program. It is mathematically proven that the program will do what it claims to do. Is that okay? Yep.
One of the things I've considered about automated program verification is whether or not the program that's doing the verification itself will also need verification.
Yes. So at some point, that.
When do you stop?
So at some point, it has to be verified by a person. It's just like programming languages, right? So you can have, you can implement another programming language using C and C++. So who wrote the compiler for C and C++?
Some guy with some really weird.
So you trace it all the way back to the time when people do not have any actual tools for programming. So in order to program a computer, you have to throw a bunch of switches to specify the zeros and ones and the address, and another push button to say, remember this. Okay, so you're programming in machine code basically. So the first program, or the first programming language, is going to be an assembler to simplify that process. Once you have programs written in assembly language, then you can have you can use that to implement simpler programming languages, like BCPL, which led to C, and then C itself can be used to implement other programming languages, possibly, I don't know for sure, BASIC, or Pascal, or something like that, and then those in return can be used to program other things. So the bootstrap is always going back to human activity. Somebody has to do it.
It'll never be entirely automated.
That is correct. But at a certain point, okay, we are hoping that we can automate this. Okay, so these are the topics that are kind of important because it brings us back to why we need to study this sort of thing. Now, what we're going to study in this class is not exactly what you need for theorem proving, but it is a good introduction to it. Okay. So the third section, section 3, talks about general propositional logic, which is basically saying, okay, what is propositional logic, the term itself, at least in the context of computer science. So in this case, propositional logic can be seen as a 4-tuple. The 4-tuple consists of alpha, omega, zeta, and iota. So these are supposed to be Greek letters, uppercase. And each one has a particular use. Alpha is the set of all the symbols to be used. Okay, look at this as alphabet. Okay, it is the alphabet of whatever propositional logic system you want to deal with. Omega defines all the operators, also known as connectives, but since we are familiar with operators, we'll just call those operators. Operators can basically join symbols together, and they can also join expressions using operators into bigger and bigger units. And then the next set is called zeta. The zeta set is a set of transformation rules. So if you can specify a filter with each rule, and you can say, if I see an expression like this, and an expression like this, and an expression like this, I can produce a new expression by rearranging things from what you start with, and then you can create a new expression. Okay, so that's why it's called the transformation rule. And then iota I is a set of a well-formed formulae. We'll explain that later on, that are known to be true. In other words, these four sets define a particular propositional logic system for basically automated reasoning. All right, so we'll go ahead and look at each one. So the key concept of propositional logic is what we know as a well-formed formula, WFF, not WTF. Okay, it's WFF, well-formed formula. So how do we define what is a well-formed formula? Okay, let's see if we can understand this thing here. So we want to define a particular predicate, which is a well-formed formula. If this predicate is true, it means whatever is in the parentheses is in fact a well-formed formula. If it is false, then whatever is in parentheses is not a well-formed formula. So the first one is an assertion. This is an assertion saying that if you pick any element in alpha, that thing by itself is well-formed. Okay. The second one is a little bit longer, but all it really is saying is you can use operators. Okay. Okay. So this requires. Let's take a look at this particular statement here. So for all I, where I is from 1 to n, you have to basically find me, this is phi. So phi I, they are asserted to be well-formed to begin with. Okay? So you have to give me n well-formed formulae. They are known to be well-formed already. So give me n of those things. Okay? The second one is I'm picking C and connective from omega n. Omega is a beta set. Omega n would be a subset of big omega, except that you're only interested in connectives that require n parameters. Now, practically for us, n can only go from 1 to 2. We have negation as the only operator that only takes one single operand. All of the other operators that we use take 2 operands. And as an operator takes 2 operands. Or takes 2 operands. Implication takes 2 operands. If and only if takes 2 operands. So practically we only have 1 and 2 being n, but in theory you can have connectives that can take any number of operands. So if you give me n well-formed formulae, you give me an operator that requires n operands or n parameters, then that particular connective, given these n well-formed formulae as its parameters, is also well-formed. That's basically what it's saying. Okay, so are we okay with this or not? Because this is kind of like a more abstract description of what is well-formed. The key idea is if you have a connective that requires a particular number of parameters, you can only supply that many operators or operands of parameters to that operator. Then that operator becomes a well-formed formula. Is that okay or not? I'll give you some specific examples later, so hopefully that will help. So just given alpha and omega, remember what alpha is? It's all the basic alphabet that you can use. And given omega, which are all the operators, you can have an infinite number of well-formed formulae that you can just generate. I'll give you an example. Let me use the tablet for this purpose. And we need to make a connection. Oh, Well, that's not going to work if it's not connected.
You just gotta use your imagination.
Or Wi-Fi, or Bluetooth, or something like that. Except this tool doesn't work, doesn't go over wireless.
Bluetooth.
Nope, not yet. There we go. Okay. So I can give you an example. Let's say alpha is defined like this. We have some constants, 0, 1 are constants. Let's say we have P, Q, and R as the other symbols. Okay. It's just, I'm just choosing to define alpha this way. And then we can choose to define omega to have the usual operators in Boolean algebra. Okay, so we can have negation, conjunction, disjunction, implication, if and only if. Let's just have just this many. Okay. So this one is actually technically in omega 1 because it only takes one operand. These other 4 ones are supposed to be in omega 2 because they take 2 operands. Is that okay? But omega itself is the union of all the smaller omegas, so it just includes all the operators. Is that okay? So if I want to be more specific, I can say omega 1 is just negation itself, omega 2 is conjunction, disjunction, implication, if and only if, and then omega is omega 1 union omega 2. It is just the union of all the omegas. Is that okay?
Yeah.
All right, cool. So just given this, okay, what kind of well-formed formula can I create? So when we look at well-formed formulae, 0 by itself is well-formed. Why is it well-formed?
Because it's empty.
No,
Okay.
not because it's empty. It's an element of alpha, okay? So 0 is well-formed, 1 is well-formed, P is well-formed, Q is well-formed, blah, 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 blah. Okay, so all of these are known to be well-formed because they are elements of alpha. No questions asked. If you are in alpha, you are well-formed. Okay?
So a single alpha is well formed.
Any element from alpha is well-formed, has a formula. Okay. So now we can say, what about this guy? Is it well-formed? Yep, because negation is from omega 1, and you just give it a particular thing that is already well-formed. P by itself is well-formed. So when you say negation of that thing that is well-formed, by itself, that is also well-formed. But I only need this much to show you how we can generate infinitely long, well-formed formulae. Because if the negation of P is well-formed, what about the negation of that? Is it going to be well-formed? It's the negation of something that is well-formed, so that is well-formed as well. So the negation of P, the negation of the negation of P is well-formed. Well, if the negation of the negation of P is well-formed, what about the negation of that? It has to be well-formed too. Okay.
Wait, so all that's well formed.
Yeah, all of these are well-formed. Are they useful? Not particularly.
Okay, just making sure that's what I was gonna ask. Yeah.
Yeah, but nobody says the well-formed formulae has to be useful. Okay? All of these are well-formed formulae. Okay? What else? What other useless things can we do?
Yeah. Oh, dang.
Is that well-formed?
That's an emoji, man.
I mean, 0 is well-formed, right?
Yeah.
Conjunction needs 2 things, right? So we can give it 2 well-formed formulae, and then connect the 2 using conjunction. So that is well-formed. So if this is well-formed, what about this?
Yes.
That will be well-formed as well, right? So I can take that and then end with itself and keep going, right? Is it really useful?
No.
No, not particularly, but they're all well-formed. So you can now think about the mechanism of making well-formed formulae and look at alpha and omega. You can just kind of in your mind say that, oh, these will span a space of well-formed formulae. Okay, where each thing in this space is well-formed. But is that thing true or false? We are not concerned yet about that part. Okay, but we have a whole space of things that are well-formed. Is that okay? Yep.
In the constraints of what like our definitions were included in module, were rules included for the order in which they have to be?
Nope, there's no ordering.
Well, what I mean is 0, 0, and.
0, 0, and.
Right? 0, 0,
That
and
depends on convention. Okay, so that's just convention that I'm using the usual convention. So if you want to use anything other than infix notation,
So you just have to specify a
right. So I'm just using the convention. I'm using a standard that is conventional to us. Okay. In other words, negation, you can always put parentheses. Okay. And then with conjunction, you can say that. Okay. So this way, you can have something like this. So this is called the prefix notation. You can also use a postfix notation if you want to. Okay, so with the postfix notation, you provide the thing that you're doing first, and then you specify what to do with it. So this will be 0 and then a negation. And then this one is 0, 0, negate. And then this one is a little bit more complicated, the last one. So the last one is going to be 0, negate, 0, 0, conjunction, and then another conjunction. It's called reverse Polish notation.
Yeah, I know about that.
You do? Okay. Who knows about RPN? Because that's not something that your generation is supposed to know. Oh, okay. Okay, cool. I'm so glad they talked about this in 430 because. Huh? It's just once you create a tree, you can traverse it any way you want, right? It's just a matter of you doing the where is it infix, prefix, or postfix in the traversal order? Okay. Well, that's why 430 is a prerequisite of this class. Yep. All right. So all of these are just ways of expressing the same thing. Okay. So I'm just picking infix because we are most familiar with infix, which also turns out to be one of the worst representation. Because infix means you can have only 2 operands, right? It's difficult to do with 3. You can because we have the ternary operator in C and C++, but it gets really kind of ugly when we have more than 2 things to specify. And then the second thing is it requires parentheses, but it can also have implied priority, which makes it very confusing. Okay? I'm just ranting here. Okay. Okay. So when you look at z plus p times q, okay, we know that we are supposed to do the multiplication before the addition, but that's a rule that we learn over time. It is not spelled out, right? If you do the prefix way, it is actually clear. Because the prefix way to do this is to say, okay, we're adding, what are we adding? Z and the result of the multiplication of P and Q. That's the prefix notation. This is the infix notation. This is the prefix notation. So the prefix notation, is used a lot by programming languages. If you think about how you call functions and utilize the result of a function as a parameter to another function, that's the prefix notation, because the function name or the method name is the prefix. And then you specify the parameters to go along with it. Is that making any sense? And Lisp makes extensive use of this thing, okay? Because in Lisp, you do not have infix notation. Even just tiny little expressions has to use the prefix notation. But postfix is even better. Because in postfix notation, this becomes PQ times Z plus. There's no implied priority of operation, and You also do not have parentheses. Yep.
Actually, we're doing it so that we keep the operands in the same order. So you could Z, PQ, and then I plus.
It depends on when you. Okay, but that part is confusing as well because it depends on the stack operation. Because when you pop the two things from the stack, Z is popped first.
Yeah.
So from that perspective, you're preserving the order of Z is the first one.
I mean, it's like you can still see it even if you choose different orders.
Mm-hmm.
But,
Wake up. There we go. Okay, so I know this is a digression, but it is not a bad digression because we are just clarifying of which notation we choose to use in this class. Okay, we just choose to use the infix notation. Okay, so but are we okay so far with alpha combined with omega can generate a space of well-formed formulae? Okay. All right. So now we look at transformation and iota. So iota is a set of well-formed formulae that are known to be true. Okay, so let's go back to my tablet here and figure out what type of well-formed formulae is known to be true. Back. That is known to be true by definition. So I put 1 into the set of well-formed formulae that is known to be true.
Why is only one open bracket?
Because I'm not done yet. Okay, I can say that is true too. Okay, I can say, well, these two, has to be here. Now, if you know that some of the variables, like p or whatever, is also true, you can also put it here. But I'm going to put something, kind of weird here. I can say p and q is true. Now, this is arbitrary, okay? I'm just saying that in this particular propositional system, I know that p and q is true, okay? Now, p and q is not as fun as some of the other ones. I can also say that p implies q is also known to be true. Now, that becomes more interesting. Because if I say p and q is true as an expression, it is the same thing as saying p is true, q is true, because that's the only way to make the conjunction true. This is more fun because if I say the implication is true, there are several ways to make the implication itself true. Maybe p is false. Okay, that makes the implication true regardless of q. But maybe p and q are true at the same time too. It doesn't say one way or another. It just simply says this particular well-formed formula is true. Don't ask me why. By definition, it is true. Yep.
could you say p omega q or something like that? Could you say p omega q?
No, because you have to use a particular connective in order for something to be well-formed. Is that okay so far? Okay. So the transformation, so we are now down to the transformations. So the transformation in zeta is in the form of this, okay? So each element in zeta looks like this. This particular symbol, okay, means, okay, there's a word for that. Consequent, it is reduced. It is matched. No, it's definitely not matched. It's it's basically a production. If you can find the patterns specified by this particular set, then this particular pattern is also, okay, I take it back. If you can find these particular patterns to be true, then this pattern is true as well. So it's a way to connect multiple well-formed formulae to another one. So look at this as a way to connect things. So I'm just trying to find out exactly what that symbol is supposed to be called. Huh? No, that may be the technical name of the symbol itself, but in the context of a transformation rule, it has a particular name. I'm pretty sure I have it somewhere. Okay, let me just fast forward a little bit. Entails, that's it. It's a silly term, you don't really have to know that. It's called entails, okay? So this is basically saying a set of psi 1 all the way up to psi m entails phi. Okay, and those are the Greek letters. Okay, so can we use some specific examples? Okay, so let's take a look at some examples. Okay, so let's switch here. So zeta can consist of these rules, right? So let's take a look at rules that we already know. Okay. So we can say, if you can find me phi and rho, I can then entail and come to the conclusion that phi and rho is true. So there are many transformation rules. This is one of the transformation rules in basic Boolean logic. Okay, hold on a second here. What is phi and what is rho? Well, they have to be in alpha too, right? So we have to make sure that these things are in alpha. So we have to say alpha is now 0, 1, P, Q, R, and then we just have a whole bunch of Greek letters, okay? We can have psi, we can have phi, we can have rho, we can have all the other ones, but we'll just start with these three. Then why are we using English alphabet and also Greek alphabet, and are they doing the same thing? What is the distinction? So as it turns out, there is a standard or there's a convention. When we use these two, they are constants. A constant simply means that once it is assigned a particular value, by definition, it cannot change. 0 cannot be, well, it can be true, it can be false. It is false. 1 cannot be true or false, it is true. Okay? You cannot say that it can be either way. These are variables. So variables, as the name implies, they can be either way, can be true or false. The value of P, Q, and R are not determined to begin with. Is that okay? So if we have constants and variables, then what are these guys? There's a special name for that. They're called schematas. Okay? Schemata. Okay? Schemata. So what exactly are those? Well, they are used as wildcards to match well-formed formulae.
Can you define the term wildcard? Make sure I'm on the same thought process here.
Okay. So variables can match constants.
Right.
Schemata can match well-formed formulae. So basically it is the placeholder for a well-formed formula. P, Q, and R, you can kind of look at those as placeholders for constants.
Right.
Constants, well, if they're not placeholders of any kind, they're concrete. Is that okay? So that is also why when you specify a transformation rule like this one, you're supposed to use the Greek letters because it doesn't matter what phi is. Okay? Phi itself can be a long expression that is a well-formed formula. Okay? For whatever reason, it is marked as true. Rho itself can be another huge well-formed formula, and also for whatever reason is known and marked as true. So what this transformation rule is saying is if you know phi is true, which can be a huge, gigantic well-formed formula in itself, and rho is also true, then we can conclude, we can entail that a conjunction of those two well-formed formulae is also true. Is that okay? Are we doing okay so far with this? But this is a transformation. It is a syntactic transformation. It is not reasoning, it is not the application of logic, it is just mechanical. Are we doing okay so far with this? Now, there are other types of transformation rules that are kind of interesting. Out of nowhere, okay, this is one of the transformation rules. Out of nowhere, which means the set of antecedents is empty, you can now say, I can entail the following is true. Whatever rho is, or the negation of rho is known to be true. Does that make sense? Without knowing anything at all, I can say, give me a well-formed formula rho, and give me the negation of that well-formed formula. I can join those two with a disjunction, and that has to be true too. Makes sense, right? So the transformation rules, before we end today's lecture, this is the one thing I want you to remember. It's the pine forest, okay? So I'm zooming out again to the pine forest. So when you look at alpha and omega, that generates, okay, the well-formed formula space. Okay? Where each thing in this space is well-formed. The best thing to do is to use color in this case. So some of these well-formed formula are known to be true to begin with. So that is your iota. These things that are given to be true is your iota. Okay? What about the other guys? If you can apply a transformation rule, okay, I'm going to use green to indicate the transformation of the application of a transformation rule. So if you say, oh, I can look at this and I can look at this, and these two will entail the following is true. Okay, whatever is true has to be well formed to begin with, which is this dot here. Okay, so there are an infinite number of dots in this entire space. So the question is, which one of these dots should be labeled red because it is supposed to be true? That's the question. So the idea is, oh, we can apply transformation rules. If you can find two dots that are red to begin with, and you can find a transformation rule that can say, oh, take this, and then the transformation result itself is also going to be true. So now we're going to label this guy to be true as well. Okay, so you can do this multiple times. Okay, so let's say this by itself implies that this is entails that one. So now you can take these two and then you say, oh, okay, we have another transformation rule that will label this guy to be true. So you can see how this is kind of like, it's kind of like a propagation of the red dots, okay? You start with just iota, those things are known to be true. The transformation rules is what allows you to propagate the red dots until you can label as many of the dots in this entire space to be red. So what is a proof? A proof is basically out in somewhere, okay? So the proof is basically saying, I got a well-formed formula that I'm interested in, okay? The question mark here is basically saying, this is the dot that I'm interested in. Is it true based on the transformation rules, the omega, and the iota that we are given with? That's the question. Can we eventually use these mean arrow stuff to label this question, this little well-formed formula that is in question, to be red? That is the question. If it can be labeled red, then you have the proof that this whatever this well-formed formula is now proven to be true. Is that okay? That is one way to look at a mathematical proof. Is, okay, sitting somewhere is a statement of some kind. I want it to be true, but how do I know that it is true? So you start with all the axioms, you start with all the definitions, and then you work with all the rules, like commutative rule, the distribution rule, and whatnot, and you just try to make connections until you can label this one to be red. Then you have proven that this statement, whatever it is true. So that is the essence of propositional logic. It's really a mechanical system that will allow you to do this. Okay? So one more thought I want to leave with you before the long weekend. Because Monday is the exam, so it'll be next Wednesday before we get back to this thing. So the problem is, the green arrows can take you to the wrong direction. In other words, oh, we are labeling a whole bunch of stuff here to be read, but it's not in the direction that you want to go. Is that okay? So now the question is, how do we fix that problem? Because what is the problem of proving theorems in your math classes? Why do we find it is challenging sometimes? You don't know which way to go, right? You know your axioms, you know how to apply the axioms, you know how to apply the transformations, but are you producing something that does not lead you to where you want to go? That is the biggest question, okay? So we have another way to deal with the propositional logic system that limits how many steps it will take to confirm whether whatever you're interested in should be labeled red or not. It will come to a conclusion within a given amount of time. So that would be really nice. Okay? So we're going to end this lecture at this point, just leave it with this picture, and then we'll continue this next Wednesday. Next Monday, once again, is exam 1, so don't forget.